we start calculation of slope and deflection for a simply supported beam, varying the flexural rigidity of beam by using conjugate beam method. In conjugate beam method, based on the two theorems, the first theorem of conjugate beam gives the value of slope, and the second theorem of conjugate beam gives the value of deflection. This is the problem having simply supported beam having a span of 4 meters and carrying a point load 100 kilonewtons at the center, and the beam is varying from A to C, 1 time of flexural rigidity, and C to B, it's varying from 2 times of its flexural rigidity. For this, we have to draw deflected shape of a beam. It's an actual beam. It's a given beam. Given beam is varying from flexural rigidity from A to C and from C to B. And now we are drawing deflected shape of this beam. A simply supported beam initially it's straight. Due to application of this point load, this beam is going to bend in circular arc shape. It's going to deflect in circular arc shape. And now draw tangent on the elastic curve on the deflected curve at A. This gives the value of slope at A. And now draw tangent on this deflected shape at B. Draw tangent on the deflected curve at B. This gives the value of slope at B. And now slope at C. Draw tangent on this elastic curve at C. And this line, this tangent is parallel to the axis of the beam, so there will be no slope at the center. At the center there will be no slope because the tangent drawn on this deflected curve is parallel to the axis of the beam. And the deflection is maximum at the center. This is the maximum deflection at the center. There will be no deflection at left support and there is no deflection at right support. And deflection is maximum at the center. And the slope is maximum at left support and right support, and there will be no slope at the center. And now we have to draw bending moment diagram for the simply supported beam carrying point load. This is the bending moment diagram, and this is deflected shape of a beam. And this is the bending moment diagram of maximum bending moment at the center. It's 100 kilonewton meter. And now we have to draw a conjugate beam. For a conjugate beam, simply supported beam is a simply supported. This is the reaction RB dash at right support. RA dash is the reaction of conjugate beam. And this is the total load. P is the total load acting on conjugate beam at the center. So this is the conjugate beam. This figure A is the actual beam. This figure B is deflected shape of beam. And figure C is the bending moment diagram. And the figure 4 is the conjugate beam. And now draw M by A diagram, bending moment by EI diagram. And now we are drawing this M by EI diagram, bending moment by EI diagram, A, C, B. Bending moment at A is 0, bending moment at C is 100 by EI. This is 100 by EI. See here, A to C, it is 1 time of flexural rigidity, and C to B, it is 2 times of flexural rigidity. There is a change in flexural rigidity from A to C and C to B, so there is a variation in the M by EI diagram. It is 100 by 2 EI. It's nothing but 50 by EI. Mark this C and mark this as a D. This is RA dash and this is RB dash. This is the M by EI diagram. Look at here guys. M by EI diagram is varying from A to C and from C to B. See in this bending moment diagram, it's constant from A to C and C to B. From here, its bending moment is varying from A to C, it's 100 by EI. From C to B, it is varying from 100 by 2 EI, because the variation in the flexural rigidity, it's varying from 100 by EI to 50 by EI. And now we have to find total load acting on the conjugate beam. This total load acting on imaginary beam on the conjugate beam, it's P. It is nothing but area of M by EI diagram. This M by EI diagram is split into two triangles. It's a first triangle and this is second triangle. A1 plus A2. A1 is off into, it's a base into height, 100 by EI. This is the area of first triangle plus area of second triangle. Therefore, the total load acting on conjugate beam, it is 150 by EI. Look at here, guys. This is the total load acting on conjugate beam. This P is the total load acting on imaginary beam. It is 150 by EI. And now we have to calculate the slope at A. Slope at A of actual beam. It is the shear force at A of conjugate beam. This is the first theorem of conjugate beam. The first theorem of conjugate beam gives the value of slope. The slope of the actual beam is the value of shear force of conjugate beam. And now we have to calculate shear force at A of conjugate beam. It is the area of M by EI diagram. It is the shear force at A. It is plus RA dash. And the shear force at B, it is minus RB dash. And now we have to calculate the value of RA dash and RB dash. And to find the value of RA dash, take moment at B equal to 0 from this figure. It's the first figure, it's the second figure, this third, and it's fourth, and this fifth figure. To find the value of reaction, RA dash and RB dash by taking moment at B equal to 0 from the figure 5. RA dash is acting at A, but we are taking moment at B. RA dash into 4, it's acting upward moment, and now it's equal to the downward moment. First triangle. It's 2/3 of its base plus area of second triangle. 2 plus B by 3. 2 by 3. From this we are going to calculate RA dash. RA dash is 250 by 3 EI. And now we have to calculate the value of RB dash. Now find the value of RB dash. Take moment at A equal to 0. We get the value of RB dash. It is 200 by 3 EI. And now find the slope at A of actual beam. The slope at A of the actual beam is the shear force at A of conjugate beam. It's RA dash, it's plus 250 by EI radians. The next slope at B of actual beam, it is the shear force at B of conjugate beam. It is minus RB dash. It is 200 by EI minus radians. And next slope at C. Slope at C at the center is 0 because the slope at C is 0 because the tangent drawn on this elastic curve at C is parallel to the axis of the beam. So there will be no slope at C. At C there will be no slope because the tangent drawn on this elastic curve is parallel to this axis of the beam. So now we find the slope at A, slope at B, slope at C. And now we have to calculate deflection at A and the deflection at B. So deflection by the conjugate beam method is going to find from the second theorem of conjugate beam method. By the second theorem of conjugate beam, deflection of actual beam is the bending moment of conjugate beam. This is the second theorem of conjugate beam. We know that simply supported beam at left support there will be no deflection, and at right support there will be no deflection. There is no deflection at left support and at right support of simply supported beam. Look at here, this is the deflected shape of a beam. There is no deflection at left support and there is no deflection at right support. And deflection is maximum at the center. That is deflection at C. It is bending moment at C. It's nothing but, I'll show you in the diagram. It's RA dash it is 100 by EI. The side of a triangle is 100 by EI. It's C dash. A to C is 2 meters. Bending moment at C of conjugate beam, it is RA dash is acting upwards, and we are taking moment at C. Distance from A to C is 2 meters minus the force acting downward. Area of a triangle half into 2 into 100 by EI. This is acting vertically down, and we have calculated centroidal distance from here to here. It is x dash. It is 2/3 of 3, 2/3 of its base. And the deflection at C is a bending moment at C of conjugate beam. It is 100 by EI. See guys, we have calculated slope at A, B, C and deflection at left support, at right support and at the center by using conjugate beam methods. Thank you guys.